What would happen if you did that without replacement, and you kind of just kept a list of people that you called? Would that
Okay,
change it?
call the college students within 5 miles problem.
Yeah.
Okay, here, let me get in here with my iPad. 608453. All right. Oh wait, I don't like that. Hang on. Okay. So repeat the question again, Josh. Sorry. Can you repeat that?
If we did it without replacement, so like we kept a list of the people that we called and we didn't call them again, because you said that was the case with this problem. So I was wondering if it would still be a geometrics situation or change it entirely.
Yeah, it would change it. It would make it more complicated. So, I mean, so in the case of the binomial distribution, like the binomial, we were doing a whole bunch of trials, and each trial was independent of any other trial. Yes. The Bernoulli experiments, those are the individual experiments, are independent of any other Bernoulli experiment. In the case of the geometric, that's the assumption also, that there's independence with each execution of the trial. But in the case of in this case right here, if I like throw out a student name every single time, do you see that the sample space is changing like dynamically with each experiment there? So like if I select a number and I look at it and I call that student and I say, well, they're out, then I would, I guess, somehow remove that from the computer database and select another one. That would change the computation. Although if the pool was big enough, it wouldn't make that big of a difference. This is called sampling without replacement versus sampling with replacement. Sampling with replacement keeps everything independent. Does that make sense? So sampling with replacement, I put the name back in and then I repeat the experiment so that independence is preserved. That's sampling with replacement. Sampling without replacement always makes things more complicated. But if the pool is big enough, do you think it really makes that big of a difference whether I put
Not really, no. Yeah.
back or not? What do you think? What do you think, Josh?
Yeah, I'm sure it doesn't make much of a difference.
No, like the computation is going to be basically, or the probability is going to be basically the same. So, I mean, we can kind of pretend. I mean, what was the pool size there? Like 3,500 or something?
Yeah, I think that was it.
Yeah, I mean, you know, you could, I guess, and what was the percentage of people that it said? Like 5?
5.
Yeah. So, I mean, you could, I guess, which means that we expect to have to get 20 deep before we start seeing stuff, right? Or before we get one. So I guess in that case, it's not really that obnoxious to assume independence, even if you weren't putting them back. I'm sure the probability would be fairly similar. But yeah, but that's a good question. That's a really big deal. By the way, that's when you do like polling, you know, for like, you know, presidential job approval or whatever it is, a lot of the probability computation is done under the assumption that each person that's polled is independent of any other person, okay? Which means that potentially Josh Mundell might get 2 calls or something, right? But in practice, that's not really what's happening. They just pick a huge sampling of 500 phone numbers or something and call them all. so that's basically sampling without replacement, right? But then all the computation is done under the assumption that each person's name was put back before the next one was pulled out. But the pool is so huge that it doesn't really make a difference that we sort of assumed that each name drawn was independent. Okay. Good question. What else? I see for the fortune cookie problem. You guys see that? Can you guys see that? Or no?
No.
Oh.
They might have sent it directly to you.
Oh, okay. Can you see that?
Oh, never mind. I can see it. Yeah. Yeah, I see it.
For the fortune cookie problem, part D, even though the expected value is 4.32, would this make sense for the question which asks how many cookies do we expect to have an extra fortune? Yeah. Yeah. So that's a good question. Didn't I think was it in this last lecture that I mentioned a lot of times the expected value ends up being a number that's impossible, like given the context? Did I say that?
It might have been the previous lecture.
Yeah, you said that in this one. I'm fairly certain.
Was it about the die rolls? I said the expected value for a roll of a die is like 3.5.
Yeah.
Obviously, that's not a possible answer. But yeah, practically speaking, Ryan, it doesn't really make sense to say, yeah, we expect to have, 4.32 cookies with an extra fortune. But that's technically the answer. But practically speaking, we might say, we expect that there might be 4 or 5 fortune cookies, with an extra fortune in them. So that's kind of practically how that works out. Does that make sense? Yes. Okay, good. Cool. All right, other questions? What else? Incidentally, I sent you an email communication about this, but Aaron Johnston and I were talking this morning during office hours, and I gave him, I think, some helpful information just about how to think about a couple of the problems, or some clarifying points. So I posted that in YouTube. It's only like maybe 10 or 12 minutes or something like that, but I think that should be helpful as you work on the exam.
Can you repeat what you said earlier about, did you say sampling without replacement means they're independent, or with replacement? What did you say there?
Well, you tell me, Aaron. So if I don't put something back, does that have a direct impact on the next one that I draw?
Yes.
Right. So that's sampling without replacement. So sampling without replacement kind of ruins independence in some sense. Does that make sense? But if I put the thing back every time I draw one, then that preserves independence with each new draw. Does that make sense, Aaron?
It
Like,
does.
every time I draw one, I put it back in, then the next draw isn't going to be impacted at all by what happened before. Okay? So this really is independence in the sense of no impact at all. Right? There literally is no impact happening if I put the things back every time. If I replace, then I'm going to have independence in that sense. But yeah, you guys know that I harped quite a bit on independence not meaning necessarily that there's no impact, but no impact implies independence. That's always true. All right, other questions? What else? What other questions do you have? Other questions? Okay, well, while you're thinking, let me just say, this is where we're gonna go moving forward. So what was the last, oh wait, independence means, so Rachel says independence means no impact on the probability, not on the event itself, right? Yes, that's what it means. So that if I have two events, you know, A and B, then A could very well impact B, but given that B happens, the probability that A will happen will not change, okay? So independence, two events being independent, means that the occurrence of the one doesn't impact the probability of the other, okay? So impact, but impact does, right, two events could be impacting each other, but then still be independent. But just because two events are independent, that doesn't mean they do not impact each other, okay? There could very well be impact. What was the example I gave to kind of show, to convince you that that was true? Do you remember? Does anybody remember what the example was that I showed you? I think in here at one point to kind of drive that home.
It was the one where it was the probability of choosing a royal card out of the deck of cards given a suit.
Yeah. So clearly in that case, you had the one event was impacting the other, right? You had the one event impacting the other, but they were still independent events. Okay. But so all that to say, independence means that the occurrence of the one does not affect the probability of the other. Okay. But that doesn't necessarily mean that they're not impacting each other. But on the other hand, if they don't impact each other at all, then they are independent. Okay, so it goes the one direction, but not necessarily the other. Can you explain the scenario again? I wasn't here for that. Yeah, I could share this and kind of show you. Now let me do this. Okay. So like A and B, let me just write this down. A and B independent means what? That the probability of A given B is equal to what?
The probability of A, right?
Yeah.
Yeah.
Or, right, there's another way you could write this. These are all equivalent, by the way. Probability of B given A is the probability of B.
Yeah.
Or the probability of A and B is equal to what?
Probability of A times probability of B.
Yeah. If one of these happens, they all happen. Okay? Any one of these implies all the other ones. They're equivalent ways of talking about independence. Okay? So in the example I gave was just, okay, if H, so the experiment was to draw a random card. Okay? Draw a random card. Okay, and then what was, so H was the event, get a heart. Get a heart. And what was the other one? Get a royal? Okay, and by the way, a royal is just Jack, Queen, King, Ace. Okay, and the picture I drew was this, like here's the sample space over here. Okay, we're dividing this thing up. Here's the hearts, here's the diamonds, here's the clubs, here's the spades. Okay, but then inside of each one of these, there was kind of a little part that was reserved for the royals, okay? Over here you have 2 through 10, 2 through 10, 2 through 10, 2 through 10, but then over here you had Jack through Ace, Jack through Ace, Jack through Ace, and Jack through Ace. What's the probability of getting a heart?
1/4.
Yeah, it's just a fourth, or 13 out of 52. Okay, well, 13 out of 52 also would have been right. And what's the probability of the royal thing?
4 out of 13.
Yeah, because there's 16 total royals out of 52, which is 4 out of 13. All right, so what is the probability of getting a heart given that you got a royal? Okay, well, if it's given, that you got a royal, that means that you're here or here or here or here. You see that? Right? If it's given that you got a royal, that means that you're only choosing from those ones. So what is this probability going to be?
It's like it's the exact same.
Yeah. Because there are 4 royals out of a total of how many? Sorry, there are 4 hearts out of a total of how many royals?
16.
Well,
Or I can't count. Maybe.
so out of
Oh, I get what you're saying.
oh wait. You're right. Sorry. Okay. So 4 out of what? 16. There are 16 total royals, 4 of which are hearts, which is a fourth, which is exactly the same as the probability of getting hearts.
So it's like the whole sample space is reduced, but all the parts are reduced equally with
Yeah.
respective to the event.
Yeah, that's what independence means. That the zoomed in sample space, like the event still eats up the same proportion of the zoomed in sample space. So that's what's happening. So what does that tell you about H and R? What did we just show? They are
Independent.
yeah. But do they impact each other?
Yes.
Hugely. Because if royal happens, I mean, look at this. Look at Aaron. If royal happens, like at this here, I was given that royal happened, right? If royal happens, don't I eliminate a whole bunch of hearts? Right? I eliminated all these. All these were kicked out. Does that make sense? All of these things were no longer possible to get. So even though there was huge impact going on, there is there's no change in the probability of hearts. That's what it means to be independent. Independent. Okay. So independent implies that the probability does not change. That's what's really going on here. But that does not necessarily mean that there's no impact. Okay, hopefully that's that's a pretty complete explanation again of what independence means. Is that helpful, Rachel? I think Rachel asked a question. Aaron, how about you? Aaron and Rachel, are you guys all right now?
Yeah, that helped.
Okay. All right. What else? Other questions? Other questions? Well, hey, thank you guys for showing up again. If you want some clarity on a couple of the problems on the test, go watch that thing, that little short little video from this morning's office hours. That should help you a little bit. But other than that, I don't have anything any more to add in here. But just okay, I wanted to point out, just moving forward, what was the last thing I talked about in the last video? Remind me, what was the very last thing? Oh, chi-squared. Was that it?
No, I don't think we got to that. We got to the we were doing the geometric thing. We did the example with the college students. It's the last thing.
The example with the college students. So we finished discrete distributions. Is that right? Is that okay? So the next thing we're going to do is we're going to move into continuous distributions. We'll talk about those. And once we get to the normal distribution, that's when we'll start really hammering some statistics home. Okay, we'll start really applying things, applying all of this probabilistic knowledge that we're gaining. Okay, so that's where that will start happening. Yeah. Yeah. Okay. Yeah, I could do that, Rachel. Sure. Although, do you click on the playlist, Rachel? Rachel said, could you possibly label the YouTube videos with the class name along with the date so it's clear which class the videos belong to? Yeah, I could do that. Although, do you click on the playlist? Or how are you getting to the videos? Because that's how I'm organizing stuff for the class. I actually have a playlist that's labeled by the class name.
Yeah, I go to the playlist.
Okay, yeah. So yeah, if you go to the playlist, all of this stuff is organized automatically.
Yeah, I normally go to the playlist after I click on today's video and it's the wrong class, and then I go, oh, that's the wrong class, and then I go to the playlist. So it'd still be nice to have the class label in there too.
Yeah, yeah. Yeah, okay, I'll do that. But just to let you guys know, I am organizing stuff by the playlists, or by the class is its own playlist. So that should help, but I will label it differently. All right? Okay. Well, anything else? Going once?
I don't know. Maybe I just am not looking at this right, but I'm on YouTube right now, and I watched an hour lecture, and it was like it ended at the chi-squared thing, and then I also saw another one that was like 45 minutes long. Did I watch the wrong lecture?
I think you did.
No wonder I was so confused that whole time. Dang it.
Oh my goodness. Yeah. Yeah, that was Aaron, that was a lecture for my theory of probability class. So
That makes sense.
there you go, my friend. Hey, just so you know, at the beginning of like almost every lecture, I'll at least say, hey, time to do some discrete math or something, just to kind of keep, just so you know. I was wondering, okay, yeah, because Aaron, you said in here that we did the chi thing. I was like, what? I don't remember doing that, but I was doing that for my theory of probability class for sure. So good job. Good job, man. I'm sorry. Sorry you watched an hour-long lecture about some advanced probability theory.
Yeah, well, cool.
Yeah. Yeah. So
I don't know how I did.
on the playlist right now?
Yeah, I'm on the playlist now.
Okay. That lecture that you watched is not there, right?
No. it's
Okay.
not.
Okay.
But it still said 2020. Isn't that this class?
No. That's
That's the year.
Oh, I thought that was a class like number or whatever.
No,
Uh,
class is 2520.
Okay,
Yeah.
gotcha. Well, I don't feel bad for not understanding that as well now.
That's all right. Yeah. Okay. Anything else? All right, guys, hang in there. Appreciate your fortitude. Keep on plugging away. Let me know if any issues come up. All right. I will see you guys later.